Looks good. Start stream. Fortunately, that means we have to stop the music. But good morning, everybody. How are you doing? How many we got? 6, 7. Are you guys in the Zoom as well? Get in there so you can see my screen. I spent all this effort getting it up on the computer. You got to see it. And it's a good thing I changed the title ahead of time. All right, so is everyone here? I need yellow group. Let's say Christian's here, Gina's here, Jose, Lewis is here, Jocelyn is there, Marichelle's there, Andre there, Angel, Angel. Okay. Yep. Leo, and let's see around some. There it is. Okay, everyone's here. Awesome. Okay, I said good morning earlier, didn't I? It's afternoon. Good afternoon, everyone. Okay. You might think we are behind schedule, but I assure you we are not, because today's class is actually fairly short, simple, and straightforward. We are talking about, as I was telling Mr. Sprunger just earlier, the special triangles. So all that Pythagorean theorem, distance formula, the triangle sum, okay, we'll draw on that today as well. We're going to put all that together and say, hey, those are really great for some circumstances. And in even special circumstances, we can do even better than that. Right? And that's where the special triangles come in. They're special because we know the shortcuts. We don't have to do any hard work. So that's algebra 2. So here we go, the special right triangles. What we know so far, as I mentioned, triangle sum tells us that for, I'm getting a lot of echo. Okay, here we go. For any triangle, given 2 angles, we can find the third angle, right? Fairly straightforward, you just subtract from 180, easy. Pythagorean theorem tells us that for any right triangle, we got to be a little more specific here. If we're given 2 sides, we can always find the third side. Right, just run through Pythagorean theorem. And that was pretty good. And even better, sometimes, if you recognize the Pythagorean triple, you don't even have to do the calculation. Saves yourself some time. So what I'm presenting to you today is 2 special cases where we can do even less work and get more information. That sounds pretty awesome. The downside is they are very specific special cases, and obviously not every triangle in existence is going to conform to these guys. But because they are so special and useful, they are much more commonly used. And so a lot of triangles you will find in real-world applications, they will purposely build them to be these triangles because they can do the math much easier. Right? They don't need to break out the trigonometry tables and look up into the calculator thing. It's like, oh, it's just this number. Right? So with these special triangles, for the special triangles, we still need 2 pieces of information. But now it can be a side and an angle instead of 2 of the same. And we can use that to find all 4 other measurements. Although really it's only 3 that are unknown, because one of the requirements is that these special triangles are already right triangles. So we already know the right angle. So given another angle and a side, we can find the 3 others. Does that sound pretty good to you? Like with no calculation, or minimum calculation if you want a decimal approximation. Here we go. Special triangle number 1 is the 45, 45, 90, aka the isosceles right triangle. And this guy is extra special because it's the only way you get an isosceles right triangle. If you make both of these sides exactly the same, of course we can't have a hypotenuse the same as another one. You can't have 2 hypotenuses, right? If these sides are the same, then these angles are the same, and they must be 45 degrees. It's the only way that will fit. So you can immediately recognize this anytime you have matching sides or the two matching angles and a right angle. It's a 45, 45, 90. And so not only do you know that this side is the same length as whatever that side is, we can also quickly determine the hypotenuse itself without having to run through the whole Pythagorean theorem formula. It's almost like another Pythagorean triple shortcut. It will work out to be every time x times the square root of 2. So whatever this side was, the hypotenuse is that times root 2. So if this was 7, this is 7 root 2. Right? If this was 12, this is 12 root 2. That's it. That's the shortcut. Right? As soon as you can see enough information to recognize this is that special triangle, you can quickly fill in the rest of them. Right? What if you went the other way, though? What if you knew what this side was, say it was y, that was given to you, then instead of multiplying by square root of 2, you would have to divide by the square root of 2, right? So that would be what these two sides are, would be y divided by square root of 2. And you might see that written as y times root 2 over 2. That's called rationalizing the denominator. It's slowly being de-emphasized in math classes. Now, way back, people had a real habit of like avoiding roots in the denominator. They didn't like that. Now we think they're okay. But you might see it still represented like this, times root 2 divided by 2. Okay? So either way, you can quickly calculate the other side. And I think the angles themselves are pretty straightforward enough, right? And if you see two matching sides, or you notice one side is the other times the square root of 2, then you can quickly fill in the angles. Oh, that's a special triangle. That's got to be 45, 45, 90. Now, do you have to memorize that? Do we need to like drill in 45, 45, 90, square root of 2? No, you do not need to memorize it. Here's why. We go back to this guy. Here is all of the formulas you will be given on the SAT right up front. And notice this corner right here, the special right triangles. They give it to you. You don't even have to remember this yourself. It's given. It's always given. It's always available for your reference. So if you ever forget, oh, that's one of those special, oh, what is the thing? It's this times, there was some fancy number. Oh, look, square root of 2. You can just look it up. However, I am going to give you a few mnemonics to try to help you remember these, because they are worth remembering just to save yourself that time of having to flip back and forth. Okay? But recognize matching angles, two matching sides. If two angles are the same, two sides are the same, that's the isosceles part. And if one of them, just think here, 180 minus 90 leaves you 90 degrees to split evenly across here. It has to be 45. Right? So it should make sense why these numbers end up the way they are. And if you have two matching angles or two matching sides, that number 2 shows up in relation to this triangle. Remember, oh, it's the square root of 2 here. Whereas the other guy has a square root of 3. We'll get to that in a moment. All right, questions so far? Anyone confused by the 45, 45, 90? No? All right. Then let's look at the other one, the 30, 60, 90. It's very similar. Right? We already know it has to be a right triangle. And if we know any one angle, we can quickly get the other. Right? Triangle sum. And if we know any one side, because of this special triangle nature, we can quickly get the other two sides. So this has, across from the 30 degree, the smallest angle is the smallest side. And across from the 60, the middle-sized angle is the middle-sized side. That's a general triangle inequality. Know that. But it turns out in the 30, 60, 90, notice you have one angle here, the 60, is twice as big as the smaller angle, 30. And the sides has a small side, big side. Hypotenuse is always the largest side. the largest is twice as big as the smallest. So that's my little mnemonic for remembering which goes where. The longest side is double the smallest side because I know the angle is double the other angle. Right? I multiplied by 2, so I multiply by 2 there. How do we remember this middle one? Square root of 3. Well, you've got a 30 here, so this gets the 30. Or you can think of it comparing to the 45, 45. Right? 2 matching angles, square root of 2. 3 different angles, square root of 3 for my remaining side. So if you could remember that, you can memorize this guy. But again, not necessary because it's always given to you in reference. So let's fill in my version here. There is no alternate name for the 30, 60, 90. No, red. So if we know this is 30, 60, 90, you can see here's the 90 already marked. I've got a smaller angle here. That must be the small value. Got to be 30. Got a larger angle down here. That must be the bigger 60 degrees. So my smallest side is down here at the bottom. Let's call that x. This is the hypotenuse across from the 90. That's always twice as big. So if this was 7, this would be 2 times 7, 14. And then across from the 60, the weird one left over, is going to be x times that weird transcendental number square root of, not actually transcendental, sorry, irrational number, square root of 3. Okay? Questions there so far? So what you're going to do with these is use them to solve missing parts. Right? In fact, that's exactly how exercises 1 through 6 start. They give you just enough information so you can tell what kind of triangle it has to be. Oh, look, these match. Right? Oh, look, these don't match. But I've got a 60 and a 90, right? Kind of fill in what has to be a result there and work out what the side lengths all have to be then. And then from there, once you know the side lengths of triangles, you can do all the same stuff. You can find areas and perimeters and all that good things. Come back to the rest of those in a moment. Because one other awesome application of this, as I said, these triangles are super common, and we literally build with them all the time because of that ease of calculation. We don't need to get into all the fancy trigonometry and stuff. In fact, we can use it to go back to the area of a hexagon, a regular hexagon. Remember when we encountered this on our, was it the surface area or the volume exercises? We had that hexagonal prism. Like, how the heck are we supposed to find the area? They didn't give us the apothem, right? We only had the side length. Fear not, with the power of special triangles, we can find the apothem. Here's how. A regular hexagon can, of course, be divided into 6 triangles. We said that was our general technique. Cut it into triangle pieces. Find the area of the triangle, you find the area of the whole shape. That still holds true. But we still need the area of the triangle. Well, what do I know about this triangle? I only know the one side length, a base. I still need that height, which usually comes from the apothem. So what I'm going to do is draw in where that apothem would be straight down, meeting the side at a right angle, by definition. So this is now the height of this triangle, but it is also the side of this triangle that is a right triangle. Even better, it's a special triangle. How can we be so sure? If you recall, the interior angle of a hexagon, we determined hexagon, you can split 1, 2, 3 into 4 triangles. 180 times 4 divided by 6 was 120 degrees. Right, would be that whole interior angle. And when I draw in this triangle, I've cut that in half. So I get this guy down here, half of that gives me 60 degrees. And so now I can recognize this is 60, this is 90, the remainder up here must be 30. I have my 30, 60, 90 special triangle. So the apothem cuts the side in half. So then this length is side length divided by 2. Half that. The hypotenuse of my 30, 60, 90 is double that, smaller side. So double of half is back to side length, which means actually these triangles are equilateral triangles all in here. That's pretty handy. So not only are we going to get the area of a hexagon specifically, but along the way we'll have the formula for the area of an equilateral triangle given just its side length. That could be neat to reference, right? Have that in your notes and you can flip back to that anytime you need it. All right, so what's left is the actual height, the final piece that we need. We have those two sides, so the remaining one must be the small side, s over 2, times the square root of 3. Isn't that neat? Now we've got it. We just know, like, that's the number. That's always the number. So the area of our equilateral triangle will be 1/2 times the base, and in this case I'm going for the big purple triangle, so the whole base is s times that height, s over 2 root 3. Simplify and combine things, we get s squared times root 3 over 4. And then the area of the whole 6-sided polygon would be 6 times that. All right, so reduce those fractions there, and you get 3s squared root 3 over 2. There you have it. Now we could go back and actually finish those questions on the volume and surface area of hexagonal prisms and pyramids. Or, going forward, you can find now the area of pretty much anything by dividing it not only into triangles, but specifically if you can divide it up into the special right triangles, you can now solve it with these tools there. Okay. Any questions so far? No? All right, then a few final comments on today's exercises. Again, the first set, finding lengths. Using those lengths to find area, perimeter, and other measurements. Notice here, right, remember you can always draw in lines. So I know these two angles here, but I need triangles. So just draw in some lines here and make things into triangles, okay? And then use the measurements you do know, right? Oh, now I have a hypotenuse, I can find the other side, and that's the same height as this, right? And work your way around there. And then we got another area here. 8 and 9 brings back coordinates, okay, mainly based on the angle. The thing to remember here is this angle is 120 degrees. Around this angle, right, halfway around would be 180 degrees. So use subtraction there and figure out how you can turn this diagonal thing here into a triangle. Okay, look for that. Look for ways to create triangles from your point. And then number 10. Number 10 is an awesome question. Number 10 requires you to really think deeply and understand not just the special triangles, but the relationship of the numbers, how to simplify radical expressions, and it brings a lot together. But it's kind of a lot to ask you in such a short amount of time. So I'm going to make this a bonus question because it's really tough. And the tricky part is not just figuring out the relationship between square root of 18 and 3 root 2, but it's how to actually demonstrate that. And I think that is the challenging part. You might know why they work that way, but can you show that? Can you create a single picture that presents it as fact altogether? And I think that's the most challenging part. It took me quite a bit of thinking to work that out. So I'm going to leave that as a bonus. If anybody wants to tackle that and think of this is just a simple square grid. They used dots. You could have actual graph paper if you want, so you can just reproduce that on your notebook somewhere. The hint, obviously, is the section itself. How can I make use of the special triangles to show this visually? So if you want to try that, go for it. I will actually give you bonus points on the homework if you can pull this off. All right? But other than that, I have no further comments on these exercises unless you have any further questions. Then I will leave you the rest of the time to work.